In this video, we'll talk about the fundamental theorem of calculus. There are actually two parts to the fundamental theorem of calculus, and in this video, we'll only be talking about part one. So quick review. When you see this notation of a long skinny s between two numbers with a function dx, what that represents is the signed area between the two limits. So for instance, this shaded area in purple, if this curve is the graph of f of x equals x minus x cubed, then this shaded area in purple down here would be the definite integral. Oh my goodness, there's a major typo. Hold on. This should be from 0 to 1, not from 0 to 0.5, because we're capturing all the area from x equals 0 to x equals 1 between y equals f of x and the x-axis. But it doesn't matter, we're not obligated to use the x letter here. Even though this function is defined in terms of f of x, I'm allowed to use other letters for my variable and my differential here. So if I had the integral from 0 to 0.5 of f of w dw, it would still represent this same shaded area, regardless of which variable I actually use in the integrand. So the variable that you're using inside the integral is sometimes called a dummy variable. It doesn't really matter that much. It just can be anything you want. And in particular, it does not have to match the same letter that you use for the formula. However, the names of the formulas do need to match. So if this is f, I can't just start talking about like q here. This has to be f also. I mean, I could have used z if I like z. It doesn't matter what this letter is. It can represent the same thing as long as this letter is consistent between the function and what you're integrating. I hope that's clear. And let's remind ourselves real quick what a function is. When we're talking about a function with one variable that takes real numbers and returns real numbers. And so basically I think of it as it has a number as input and a number as output. And so anything where you can tell me a number and I can tell you a number back and that's consistent is a function. So this is a function that you probably weren't expecting, but I can define a function. So this is a function you probably weren't expecting, but I can actually define a function in terms of the definite integral of another function. So in this case, I have g of x is equal to the definite integral from 0 to x of f of t dt. Now notice, if this were 0 to a number, then this would be a number as output. So as soon as you tell me the value that you want to plug in for x, I know that there is a number that represents. So this expression is actually a function of x because you can plug in a value for x and get a number out. So for some examples of that, like what if we let x equals 0.25? Since we're plugging in x equals 0.25, then g of 0.25 would be the definite integral from 0 to 0.25 of f of t dt. And this number, whatever this answer is, would correspond to this shaded area. We could do a similar thing with another number, like we could say, let x equal 0.5, and then we would be looking at the definite integral from 0 to 0.5 of this f of t dt. And then I'd be looking here at this shaded region, which is larger than it was before. But the important thing is that this is a function of x, because as soon as you pick a number to go here, you know that you're looking at some shaded area, and you can determine what that number is in theory. Now, if you're in this class, you've taken something about derivatives. And so you should be thinking, as soon as you learn about a new function, the first question you want to ask is, what is its derivative? How would I find the derivative of this function? And in this case, it turns out it's really easy. So when you have a function that's defined in terms of a definite integral of another function, where the limit of integration is the variable that you're plugging in, when you're in this situation, the derivative is just whatever you were taking the definite integral of. Let's say this precisely. So if f of x is a function that's continuous over an interval a, b, and the function g of x is defined by this expression, where g of x is the definite integral from a to x of f of t dt, then when we take the derivative of g prime of x, we just get original f function. Now you have to be a little bit careful here because we are mismatched on the variables. We have an x here and a t and a dt here, but then we have an x here and here. And that might be a little bit confusing, but just remember that since g is a function of x, whatever its derivative is will also need to be a function of x. So let's look at g of x is the definite integral from 1 to x of sine of t squared dt. And let's ask, what is g prime of x, the derivative of this g of x function? Do you know what it would be? Yeah, it's just going to be this expression, sine of t squared, but with x instead of t. So the derivative g prime of x would be equal to sine of x squared. Now there's nothing here that says I have to use t. So what if I defined this function d of x to be equal to definite integral from 0 to x, e to the sine of r, dr. So here the dummy variable for the integration is r. What would d prime of x be? Well, it would be e to the sine of x. I'm just taking this integrand and replacing it so the variable is equal to x, and that is the derivative of this function defined in terms of this integrand. Finally, we can let q of y. There's nothing that says I have to use x as the input variable either, and there's nothing that says I can't use x as the integrand variable. I just can't use x for both of them at the same time. But let's say that q of y is equal to the definite integral from -2 to y of sine of cosine of x squared plus 4 dx. So you probably know the question that's coming, and you may already know the answer as well. Question is, what is q prime of y? And the answer is, uh-oh, there's a mistake here. Look carefully. This should be sine of cosine of y squared plus 4. Q is a function of y, and that's what changes as we change this variable. Then the derivative should also be a function of y. So be very careful here. I know there's a lot of variables moving around and a lot of things that could happen, but whatever the limit of integration that defines the function is, that's also going to be the variable that shows up in the function and in its derivative. So it can't be x here, it should be y. So that's part one of the fundamental theorem of calculus, and it's relatively straightforward in its basic formulation. In the homework, you'll see a few more exercises where there are some tricks that involve changes to the upper and lower limits. But for now, I think this idea of an area accumulator function